Assalamualaikum warahmatullahi wabarakatuh.
Good morning, ladies and gentlemen, dear staff members, and fellow friends who are able to join with us today in today's event.
First thing first, we would like to say the utmost gratitude towards God for letting us gather in today's event with a good and stable health conditions. Welcome to the day 2 of International Conference on Advanced Technology and Multidiscipline 2023. Before we start the event, there's an old saying in bahasa that say tak kenal maka tak sayang. So let us introduce ourselves. My name is Yuriso Jinarita Tanamal, and here with me,
And I'm Zifa Sholima, as Masters of Ceremonies who will guide ICATAM's proceeding today. Ladies and gentlemen, for today's agenda, there will be 3 plenary sessions led by 3 keynote speakers and moderator. For the first session, all the way from Japan, from one of the top world university, Tokyo University, and be brought by Dr. Takeshi Kondo, the topic will be about boron-doped diamond powder nanoparticles as functional electrode materials. The second one will be from one of the top university from Indonesia, Universitas Airlangga, and will be brought by Dr. Tata Amrila. The topic will be about thin film nanotechnology for renewable energy. And the third one, all the way from New Zealand, Auckland, will be brought by Dr. Ramon Zamora, and the topic will be about DC microgrids for better and cleaner energy utilization.
so ladies and gentlemen, without waiting any longer, let us move forward to the first topic, which is continual machine learning, boron-doped diamond powder, or nanoparticle as functional electrode materials, and let us welcome our moderator for this session, Ms. Prastika Krisma Jiwanti, PhD.
Good morning, everyone. Okay, ohayo gozaimasu, Kondo sensei. Can you hear my voice? Good morning, Dr. Kondo.
Can you hear me?
Okay. Hi, so my name is Prastika and I'll be the moderator for these sessions. So before we proceed, I'd like to introduce our keynote speaker for today, Associate Professor Dr. Takeshi Kondo. So he finished his bachelor and master and also PhD from the Department of Applied Chemistry, Faculty of Engineering, the University of Tokyo, one of the best university in Japan. So currently, he's working as an associate professor at the Department of Pure and Applied Chemistry, Faculty of Science and Technology, Tokyo University of Science. So his research mainly on the boron-doped diamond nanoparticles for sensor and catalysis applications. For today's talk, he will deliver a lecture about boron-doped diamond powder or nanoparticles as functional electrode materials. So Kondo Sensei, you have about 50 to 55 minute presentations, and the last 5 minutes is for Q&A. And all the participants, you can drop the Q&A or the chat box. So please welcome Dr. Takeshi Kondo. Time is yours. Yoroshiku onegaishimasu.
Okay, thank you very much. So I will share my slides. Okay. Okay. Okay, thank you very much for a nice introduction. I'm Takeshi Kondo from Tokyo University of Science. And first of all, I would like to thank the committee for giving me this special opportunity to present my talk as a keynote lecture. And my talk today is boron-doped diamond powder nanoparticle as functional electrode materials. So this is the content of this talk. And at first, I will introduce boron-doped diamond electrode as a functional electrode material. Okay. So we focused on the diamond as an electrode material. So diamond is, I think everyone knows that this is one of the allotrope of carbon. So carbon has many allotrope like this, and usually they use sp2 carbon materials such as glassy carbon and carbon black or carbon nanotube graphene as an electrode material. And so we focused on using diamond. So the diamond is crystal of diamond carbon with three-dimensional network, unlike the sp2 graphitic carbons, which has two-dimensional crystal. So they are very different. They have very different properties. And this table shows properties of diamond, physical properties of diamond. So many people know that diamond is very hard material. It has largest, most hardness among the materials, and also diamond has the largest heat transfer coefficient and smallest thermal expansion coefficient. Like this, the diamond has very extreme physical properties, very extreme. And also, diamond is very inert material. So it is chemically inert. So, and resistant to acid, alkaline, or alkaline and organic solvents. The diamond is very stable material. And also diamond is inert. So this is non-toxic material. So it has very good biocompatibility. So I think, so we believe that diamond is the king of materials with very extreme properties and very good inertness and good biocompatibility. So we would like to apply this good material, diamond, as an functional materials. So again, diamond has very unique superior properties like extreme physical properties, chemical inertness, and good biocompatibility. And diamond is made of carbon, which is abundant material, so abundant element. So we can synthesize diamond from carbon source, many carbon sources. So we'd like to apply this material to functional materials for a wide range of fields, including medical, biological fields, energy devices, electronic devices, electroanalytical devices, and environmental purification systems. But we need to obtain some technology for application of diamond to functional materials. So we focused on the investigation on diamond synthesis and fabrication and surface modification. And so we try to combine diamond with other materials to create a new functional materials. Then also we focused on electrochemistry. So we use boron-doped diamond, which is a conductive diamond. So as you know, diamond is a very good insulator. So very high, it has a very high resistivity. But when doped with boron, this can generate holes and the conductivity increased as a boron doping level increased. So you can use this material for electrochemistry. So again, diamond is insulating materials. When you dope boron at a small amount, it shows p-type semiconductor. But the heavily boron doped diamond shows very good conductivity. So you can use this material as electrochemical electrodes. So how to dope boron to diamonds. So you can synthesize diamond with carbon source containing some boron source. So we use this type of chemical vapor deposition system, which is microwave plasma assisted CVD system, to form our diamond film on the substrate material. So we use a carbon source. We use acetone and methanol mixture as a carbon source, and we put this compounds, 3-methoxyboron to this solvent. Then the carbon and boron source was evaporated by hydrogen gas bubbling. Then we put these compounds into this plasma chamber. So you can form diamond films on the substrate material. So this figure shows a typical photograph of polycrystalline beaded surface. So you can obtain polycrystalline beaded thin film on a substrate material such as silicon wafers. So you can see some crystal facets of diamond and very dense polycrystalline film. So this film is very conductive, so you can use this material for electrochemistry. And this is some plate type thin film, so this can easily utilize for electrochemistry. And the diamond beaded thin film electrode shows a very wide potential window. So this is cyclic bottom grams of diamond electrode in sulfuric acid. So diamond has very wide potential window. Potential window means the potential range where oxygen evolution nor hydrogen evolution does not occur. So you can use very wide potential range for such as electroanalysis. And the CV has also has low background current. So for other typical electromaterials, there you can see some current here within the what potential window, but for diamond, the background current is very low. So that you can, if you use this for electroanalysis, you can obtain very good signal to background ratio. And also, this is diamond, so basically this material is very physically or chemically stable. And also this has very good biocompatibility. You can use this electrode for some bio-related sensors. And also diamond surface is very inactive to adsorption. So this surface is has good anti-fouling properties. So I mean, proteins or some surfactants do not absorb on the surface so much. So you can use this electromaterial for such electrolytes, including proteins or surfactants. So this is one example of electrochemical application to electroanalysis, application of BDD electrodes to electroanalysis. This figure shows cyclic bottom grams for some DNA and RNA. So you can see in the case of glassy carbon electrodes, which is typical electrode material, you can see this anodic peak for guanine. And in the case of BDD electrode, you can see two peaks here, guanine and adenine. So this is because this electrode has a wide potential window at this high potential region. So you can see this peak at very high potential, which cannot be observed for glassy carbon electrodes. And also background current is very low, so you can see very clear peak here. And this is also application of BDD electrode to electroanalysis. This is detection, electrochemical detection of histamine. And so at glassy carbon and diamond, at both electrodes, another peak was observed. But in the case of diamond, so background current, this blank data, background current is very low, so signal to background ratio is very high at BDD electrode. So you can obtain very good signal to background ratio. So the diamond electrodes, BDD electrodes, is very useful for electrochemical detection, especially at low concentrations with a nice SB ratio. So this is another example of application of BDD to electroanalysis. This figure shows differential pulse anodic stripping voltagram of lead ions. So this has very anodic potential at very low potentials, but and for other electrode materials, there are very significant hydrogen evolution reaction can occur. But in the case of diamond, it has very wide potential at this lower potentials. So you can see very good and stable another peak for lead. So you can use this material for detection of such base metal ions. So you can use this electrode material for a wide range of analytes, from metals, ions to some organic compounds. So this is another example of application of BDD to electroanalysis from electrolyte containing some proteins or some surfactants. So in the case of glassy, this is a square wave protograms for ascorbic acid, and at glassy carbon and carbon paste electrode, so the peak was not stable in the electrolyte containing these compounds, but in the case of diamond, the peak was very stable. So this is because BDD is very resistant to electrode fouling due to poor surface absorption properties. So you can use this material for many types of samples which contains proteins or some surfactants. Okay, so when some compounds or some polymers was absorbed on the surface of BDD, you can decompose some such materials from the surface to clean the surface by applying high potential. This is application of BDD to HPLC electrochemical detector. When this is a repeated analysis of some chlorophenol compounds. In the case of glassy carbon, the current response decreased gradually due to surface fouling by oxidized compounds of this polymerized material. But in the case of diamond, this is the current response was very stable because due to poor electrode fouling. And also you can clean the surface by application of very high potential at very short time. So this is another example of application of BDD. So so many researchers are applied BDD to electrolytic water treatment. So at BDD electrode, some organic compounds in electrolyte can decompose completely into CO2 by applying the very high potential for a long time. So especially at BDD electrode, it is known that OH radical can generated efficiently at BDD electrodes because the interaction of electrode surface and OH radical is weak at BDD electrodes. So this can be used for decompose of some organic compounds very efficiently. So also BDD is very stable material. So tin dioxide is also a type of so-called active electrodes, and so at both electrodes, phenol can be decomposed at very high degradation ratio. But for long service life, tin dioxide can be deteriorated at short time. But in the case of BDD, you can use this material for water treatment for very, very long lifetime. So BDD is a very promising electrode material for electrolytic water treatment with high efficiency due to efficient OH radical generation and very good stability. Then also, BDD electrodes is known to generate ozone at very high efficiency. So this is one example of application of BDD to ozone generator, electrochemical ozone generator. They use BDD film with many holes, and they create zero gap electrolytic cell. You can generate ozone from pure water without electrolyte. Then also BDD electrode is known to show very good efficiency for electroreduction of CO2. So CO2 reduction is a very important topic for carbon neutral technology, and BD has very unique property that has very good phasic efficiency for CO2 reduction because of wide potential window. Simultaneous hydrogen evaporation can be suppressed, and it depends also it depends depends on the condition, electrolysis condition, but in some case, you can obtain formaldehyde at very high Faraday efficiency. And also, in many cases, you can obtain formic acid from CO2 reduction. So now, as I told, so BDD electrode is very nice electrode material with very unique properties based on the wide potential window and low background current and very good stability and electrode fouling resistance. So one disadvantage of diamond electrode is that this is a very hard material, and this type of very flat thin film. So you can obtain a thin film PDD, thin film on a substrate material. So you need to use some substrate, but this limited to silicon or niobium and etc. So they are very hard material. They also the BDD synthesis requires high temperature process at 800 degrees Celsius or higher temperatures. So you cannot obtain arbitrary size or shape of electrodes easily. And so in order to this very good, nice material to wide range of electrochemical applications, we created BDD powder as an electrode material. So this is conventional thin film electrode, but we created a powdered BDD electrodes. So this is a conductive diamond powder, and you can obtain arbitrary size from several nanometers, 100 nanometers to several tens of micrometers. And this material can be made into a composite with other materials to create a new composite material. So again, BDD has very good properties such as wide potential window, low background current, physical chemical stability, and biocompatibility. And so we can add another properties. This is such as a large specific surface area and this is powdered material, so you can apply these materials to printed electrodes or painted electrodes. So this situation should expand the wide application area to widely further. So this is how to make BDD powders. This is exactly same as the method that we create. We synthesize diamond film, but we use diamond powder as substrate. This is a commercially available insulating powders, and we deposit boron double diamond layer on the surface of particle. Then we can obtain conductive powder, which has a very good conductivity. And you can choose very different sizes of diamond powder of substrate, and you can obtain arbitrary size of BDD powder. So as you can see, this figure shows a SE image of diamond powder substrate and BDDP after CVD process. So there are almost no change in the size and shape before and after CVD process, but some morphology changed by BDD nanocrystalline deposition, and the conductivity is very different. These are insulating materials, but they are conductive materials. So you can obtain arbitrary size of powders by choosing substrate size. Okay, this is close image of SEM, so you can see the change in morphology. So because the particle was coated with nanocrystalline PDD thin film. So this figure shows size distribution of PDD P from upper panels shows distribution of diamond powder substrates, and lower panels shows the distribution of BDP. So you can see slight shift of mean diameter, but the distribution maintained. So this also shows that you can obtain desired size of BDP by choosing corresponding diamond powders. So this shows Raman spectra. Generally, so you can obtain good quality of diamond BDP film by using large size powder. So this contains some sp2 carbon species, which should be should exist on in grain boundaries of nanocrystalline between nanocrystalline BDDs. But anyway, you can use this electrodes for material for diamond electrodes. So the next, I will introduce some application of BDD powder to electrolysis and supercapacitors. So at first, I would like to introduce application of BDDP to electrolysis. So as I told, PDD is very good material for electrolytic water treatment because it can generate ultraradical at very high efficiency, and also PDD is a very stable material. So you can use this material for a long time as water treatment anodes. So we apply BDDP to electrolytic flow cells. So we use BDD powders with several tens of micrometers, relatively large size powders, and we created a packed bed of BDP on a here is a ceramic filter, and so we use this packed bed as a porous electrode material for electrolytic water treatment flow cell. So this is an example of experiment using methylene blue, which is an organic dye, blue color dye, and so this was used for as a model organic pollutant. So this is before application of voltage, and after some application voltage, you can see the methylene blue solution flow like this downwards. Then after passing through this BDDP packed bed, the color was color changed. I mean, so as a decolored after the through this packed bed. This means methylene blue was decomposed into non-color compounds. Okay. So at first we check the effect of BDD packed electrode. So we change the amount of BDDP packed as a bed. And so this figure shows relative methylene blue concentration as a function of electrolysis time. So this indicates that the larger amount of BDDP was effective for decomposition of methylene blue. This means BDDP packed bed worked as an anode, a porous anode. So we also check the formation of OH radical by using our chemical probe, sodium terephthalate. So this compounds can react with OH radical to form HTA. And this compound shows fluorescence at this wavelength. And so we confirm that OH radical generation after application of 5 volt for 30 minutes and sodium sulfate electrolysis. And the peak intensity increased as a function of the amount of BDD used. So we can conclude that OH radical was generated in the entire BDD packed bed. So, and also we check the effect of flow rate to the degradation rate. So we found that faster flow rate is effective for a swift electrolysis of methylene blue. Also, we check the effect of amount of BDD for flow cell type experiment. So this is a batch cell without no electrolyte flow, and we checked. This is a flow system, and in the also in the flow system, the larger amount of BDDP is effective for a fast degradation rate. So this is a video of measurable degradation with BDD packed electrode, and here. So you can see the decorrelation of methylene blue during the electrolysis at this flow systems. Okay. 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 So we can obtain colorless electrolyte after 15 minutes electrolysis at this system. So very small amount of BDD is here, packed bed, but so this is very effective. So also we did a repeated electrolysis test to estimate the stability, durability of these materials. So we did test for 1 hour. Then we change the new solution to a new solution, and the test was repeated several times. So at fourth test, so the degradation rate decreased like this, but after prolonged electrolysis to low concentration, then we changed the solution. So the degradation rate was improved to almost initial proper performance. So this can be used. So we think this material is very durable to electrolysis at high voltage for a long time. Okay. So finally, I would like to introduce my application of BD bonded nanodiamond to supercapacitor. Okay, this is one example of application bonded diamond to energy devices. Supercapacitor or electric double layer capacitor is known to be a kind of energy device, electro energy storage device. So, which has two electrodes and separator and electrolytes between. Then, when you apply some voltage between two electrodes, electric double layer can be formed on the surface of the electrode to accumulate charge, and you can use this charge for electricity. So, and basically the supercapacitor does not involve chemical reaction. This is a physical reaction. I mean, just absorption. So you can use this charge discharge cycle at very large number of cycles without significant deterioration. But the problem is this can this can store very small energy. So this figure shows Ragon plots showing specific energy and specific power. In the case of secondary batteries, they can store very large energy, but the power is low. But in the case of capacitors, they cannot store so much energy, but they has very high power. So now we are trying to improve the specific energy of electric EDLC by using BDD and aqueous electrolyte. So for conventional EDLC, they use activated carbon as an electrode material and organic electrolytes for electrolytes. But in this study, we use BDD as an electrode material, and this shows a very wide potential window in aqueous systems. So we can use aqueous electrolyte for electrolyte with relatively large cell voltage. So there are many research on porous BDD for EDLC. Honda Sensei created this type of nano honeycomb diamond film for EDLC, which has very high specific surface area. And also we have created this type of porous BDD film for EDLC with very large surface area. Also, other group has tried to create such as porous BDD electrodes, and they all showed wide potential window in aqueous electrode. So all we have to do is to create a large specific surface area BDD material. So we have developed a new conductive diamond material with a large specific surface area. We use a nanodiamond as a substrate. Then we deposit bonded diamond on the surface of nanodiamond. So this is commercially available nanodiamonds. It has a primary particle size of 4 to 5 nanometers, and we use this material for a substrate of conductive nanodiamond. So we deposit a BDD via CVD system, but in this stage there are very much amount of sp2 impurities. So we minimize the amount of sp2 carbon impurity by oxidation in air at 455 degrees Celsius for 8 hours with a muffler furnace, and we obtained heat-treated BDND, boron-doped nanodiamond. Then we use this material for electrochemistry. So this is a very simple illustration, but actually the nanodiamond was an agglomerate in a dried state. So in some dispersion in water, this can disperse as a primary particle, but in this dried state, this forms a agglomerate. So we deposit BDD on the surface of the agglomerate, and this contains BDD and some graphitic carbons or amorphous carbons on this as deposited BDD. So we apply heat treatment in air to decompose vulnerable carbon species such as amorphous carbon. So after this treatment, BDD, so diamond structure and some very stable sp2 structure was left, and we use this composite material for electrochemistry. This has very high specific surface area, up to 650 square meter per gram, and very large conductivity of 0.5 Siemens per centimeters. Then at first we check the electrochemical property of this material, this new material. So we put BDND, boron-doped nanodiamond ink, on the surface of graphite carbon, which is a current corrector. After dryness, this ink was covered with Nephron, and we obtained a test electrode for BDND. This figure shows cyclic bottom grams in 3 electrode system using reference electrodes, and lower panel shows the CV of a 2 electrode system, symmetric 2 electrode system. Then in the CV for 3 electrode system, you can see very wide potential window of BDND, more than 2.5 volts But in the case of activated carbon, which is usually conventionally used for capacitors, it has only 1 volt potential window. And in the case of two electrode system, the activated carbon showed 0.8 volt of cell voltage in a sulfuric acid system. But in the case of BDND, it shows very large cell voltage up to 1.8 volt, even in sulfuric acid solution. So since the energy stored in the device is directly proportional to the square of cell voltage, so this is very effective. So this figure shows a capacitance which was estimated from the result of CV as a function of scan rate of the CV. So in the low scan rate, the capacitance was larger at activated carbon, but in the case of a higher scan rate region, the capacitance was larger at BDND. So this is because activated carbon is basically very porous. I mean, this contains very much amount of micropores inside the relatively large particles, but BDND is very small particles, and so this should be good for a high power rate. And we calculated energy density by using this equation, and we used 1.8 volt for BDND and 0.8 volt for activated carbon. So we found that the energy density was much larger at BDND, the device of BDND, due to this factor, cell voltage factor. Then, so next we, in order to further expand the cell voltage, I mean expand the potential window, we change the solution from sulfuric acid to saturated sodium perchlorate. This is known as a very as an electrolyte with a very wide potential window. Then by using this solution electrolyte, the cell voltage was found to be very large, up to 2.8 volt. But in the case of activated carbon, also this device shows very wide, very large cell voltage. So this type of electrolyte is so-called water in salt electrolytes. So saturated sodium perchlorate contains so much amount of ions in the solution. So almost all water molecules has interaction, strong interaction between these ions, electrolyte ions. So the amount of free water molecules is very low. Very much amount of water molecules is coordinated to ions. So
Me, Dr. Kondo, you have 5 minutes left. Thank
okay.
you.
So so in order to decompose water from this type of water, you need high large over potential. I mean, you need very large activation energy to decompose this into hydrogen and oxygen. So this electrolyte has a very wide potential window. Anyway, so this is also a Raglan plot showing power density and energy density of the device using BD. So by using BDNOD as an electrode material and saturated sodium perchlorate as electrolyte, you can obtain very large power and large energy density. So we can conclude this combination is the best for high power, high performance aqueous EDLC. So we also try to fabricate some very simple BDND EDLC cell with this type of very simple system. Then we check the effective concentration of the sodium perchlorate electrolytes. So we found at lower concentration, the cell voltage was low. But in the case of a higher concentration, it shows very large potential cell voltage, which is effective for large energy storage. So we calculate the capacitance and energy density as a function of current density. This is estimated from the result of galvanostatic charge and discharge experiment. And we found that 8 molar of sodium perchlorate is very good for high energy density especially at high current density. I mean, this shows very good energy and power density. Then also we check the durability of this device containing BDND for electrode material and 8 molar sodium perchlorate as electrolyte. So we repeated this charge discharge up to 10,000 cycles, but the capacitor retention was very good. Also, this figure shows flow test, the result of a flow test, and more than 90% was retained after 10 hours after application of this high voltage for 10 hours. So this system has showed very good stability. Okay, so I have to conclude this talk, and today I introduced bronze nanodiamond powder and bronze nanodiamond nanoparticle as new functional electrode materials. So they showed basic properties of diamond, bronze diamond, but they are powder material or nanoparticle materials, so they can use apply to new devices such as BDD packed electrodes for electrolysis and EDLC, electric double layer capacitor, for very nice high performance aqueous EDLC with high power and energy density. Okay. So since this material is very basic materials, just conductive diamond powder, so you can use this material for many types of applications, from sensing devices and some energy devices such as not only supercapacitor, but also we try to use this material for cathode catalyst support. And also we created very large size electrode by spray coating of BDD P ink, and this can be used for a very good anodes to create to form peroxide disulfide from sulfuric acid. So many collaborators are using this material. So if you're interested in this material, please contact me, and I'm very welcome to collaboration. Okay, so thank you very much for your kind attention.
much, Kondo Sensei. Very interesting work. Okay, so we are here. There is questions from the participants. Okay, I will read this. So thank you very much for your interesting talk. May I know how do we modify BDNP for DNA or RNA detection, and what are the functional groups shall we graft to BDNP? Thank you. Hi, Dozo.
Okay. So basically, so at first, as deposited, as grown diamond surface has hydrogen termination, but it can be converted to oxygen functionality. So with some a simple oxidation process, so you can use such functional group for grafting, and also so many researchers use some amidation of diamond by using some allele diazonium method. So I mean, you can graft diamond surface with phenyl nitrophenyl group, and you can reduce the nitro group to amine group. Then you can use the amine group on the surface for grafting with some bio-related compounds such as DNA or some enzymes or other bio-related compounds.
Okay. Okay, so I think it's very possible to modify the BDNP with DNA by some functional groups.
Yeah,
Okay.
there are some many research for diamond films, so you can apply such method to diamond powders also.
Okay. Okay. Is there any more questions from the participant, please? Any question? Oh, the next one. How important is the morphology to the sensitivity of BDD? From Dr.
Okay.
Kahta here. Okay.
Yeah. So I think I think morphology may contribute to the sensitivity. So usually, so I think if you have a very large specific surface area with some structures, nanostructures, it causes increase of background current. So I think, so in my opinion, the flat surface is very good for sensitivity to reduce the background current.
Okay.
Yeah.
Okay, so thank you. Okay, the next question from Laurencia. There are two questions. The first one, is there an order in mixing BDD and P, isophorone, methyl ethylcathone, and resins? I think it's to make BDD ink. Yeah. And the second one, how do you prevent BDD P ink from clumping? Okay.
Okay. So for the order, at first, resin is basically we use solid resin. So we dissolve resin by methyl ethyl ketone, and the isophorone is so it's also a solvent. So at first we dissolve resin by methyl ethyl ketone, and we added isophorone to prepare a solution. Then we mix BDD powder into the mixture of solvent. And so the solvent can easily evaporate to time. So you have to add additional isoporon or to keep the solution at some volume. Okay.
Okay, thank you very much. Is there any more questions from the participant? Oh, okay. Is that possible to make an epitaxy BDD film or single crystal? If so, is the epitaxial BDD film better than we use nanostructure BDD film? I guess nanostructure BDD film has larger surface area.
Yes, it depends. At first, you can synthesize epitaxial BDD film on a single crystal surface. Yeah. Actually, I did it. I have created such a BDD film, and for application, it depends on the application. So, as I told, the epitaxial film has very flat surface. So I think it was very good electrode for electro analysis with due to very low background current. But in some cases, if you want to large surface area, surely nanostructure BDD film is best. But I don't know. So for electroanalysis, I think it depends on the analyte or the mechanism of the electroanalysis. I cannot say which is better, single crystal or nanostructure BDD. It depends on the analyte or mechanism of electroanalysis.
Okay. Okay, so is it okay for one more questions? I think. Could you please scroll up? Sorry. Okay, from Anggi. So I'm currently working on using BDDNP as modifier for SPE to detect propanediol organic compound. I tested the electrode using CV and DPV methods, and I found there is no new peak detected, and the analyte is added onto the electrode. So my questions, there is no distinguished peak shown through those electrochemical measurement methods. Maybe why it's happened like that.
I don't know, but yeah, this is a very specific question, and
So there's no very specific.
currently I have no idea, but
Yeah.
We can discuss if you show some data. I'm very happy to see your data, so we can discuss later.
Okay, so maybe Anggi, you can drop email to Dr. Kondo. Okay, so the last questions, I think, you use isophorone and methyl ketone in very small amounts, and both are very volatile. How to keep BDDNP ink the right consistency as an ink?
So, so actually, this solvent is very volatile, so they are completely evaporated after printing. So after dryness, it remains only BDDP and resin will be left on the surface. So you can add these solvents during your process. So as you want. Yeah.
Okay.
So I do not the amount of methyl ketone and isophorone is not so strict. You can put them into the ink during the process.
Okay. Okay. Yeah. So.
The ratio of BDP and resin is important.
Okay. I think it's clear enough. Okay, so we are running out of time. So the participants, if you still have any questions, you can drop your questions by email, I think, to Kondo Sensei. Okay,
Yes.
so before we close these sessions, I would like to give a certificate of appreciations.
Okay.
Okay, so thank you very much for your nice talk today. Hopefully, maybe for the next time, we can welcome you directly at the Universitas Airlangga. So thank you very
Yeah,
much.
I hope. Thank you.
Hi. Okay, so thank you very much. Then we close this session. Good morning, everyone. Hi, thank you so much. ありがとうございました。
ありがとうございました。
Once again, thank you Mr. Takeshi Kondo and our moderator, Ms. Prastika, for the interesting session earlier. Ladies and gentlemen, we'll have a 5-minute break session. Please be back at 10 Indonesian time. There will be also a video profile and committee's announcement following this. Ladies and gentlemen, welcome back to ICATAM 2023. Moving on, we will proceed our second plenary session with the second topic, thin film nanotechnology for renewable energy. And for this, let us please welcome our moderator for this session, Dr. Raden Djoko Kunchoroningrat Susilo.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. Now it's turn for Mr. Tata Amrila PhD to show his presentation. Mr. Tata Amrila PhD earned his bachelor degree at Institut Teknologi 10 November Surabaya, Indonesia. And furthermore, he earned his master and doctoral at National Chiao Tung University from Taiwan, followed by visiting student in Max Planck Institute for Chemical Physics of Solids from Germany, and visiting scientists in Universitas Negeri Malang, Indonesia, and continue by postdoctoral appointment in Advanced Institute for Material Research and Core Research Cluster, Tohoku University, Japan. So he has many experience. He is currently as an assistant professor in Universitas Erlangga, Indonesia, especially in nanotechnology engineering. And then his area of interest include the fabrication of nano-sized material, the properties of oxide, metal alloy, organic, inorganic compound, and the study of how small size affect the exotic phenomena. Today he will present about thin film nanotechnology for renewable energy. So, Mr. Tata Amrila PhD, please take your time.
Okay, thank you so much, Dr. Joko, for the introduction. And thank you also for the committee that who invite me as invited speaker today. Let me share some presentation about what I will discuss today. The title of the talk is about the thin film technology for electronic and renewable energy. Yeah, this is the discussion, and the presentation is mostly related to the research that I did in the NYCU, or National Yang Chiao Tung University, Taiwan, and then PMR in the Tohoku University, Japan. Okay, before I discuss more deep about what is the application of thin film technology, here I would like to discuss about the perspective of the thin film. For example, like actually, the thin film technology is related to how we make some devices. The devices to for some application. Yeah. For example, like electronic devices. For example, like in the right side of the figures, shows the combination of some materials, namely gallium manganese arsenide, gallium manganese arsenide, and gallium arsenide beryllium, yeah, that they combine for this four of these materials into some function. Yeah, it's actually similar to that Lego house. For example, like if there are some rooftop, right, and then there is some wall, and then there are some underground like this one. For this combination, they have some function, and then they can build it as a house that can be used as a function, something like that. It's also similar to that thin film technology. Actually, we can deposit some layer by layer, some materials to have some function. For this one, the combination, layer combination of the gallium manganese arsenide and gallium arsenide is related to the electronic devices. We call spin electric double layer transistor. Actually, the thin film technology also is not related to the material functionalities, yeah, but it's also related to the how we develop some materials and then how we discovering some new materials. And then I will discuss later. As for the function of the thin film technology, there are actually so many, yeah. not related always, not always related to the electronic devices, but also related to the energy, related to the environment. For example, like in energy, I think you already know about the solar cell. The solar cell is a combination. Actually, the solar cell is consists at least two materials that they have N-type semiconductor and then P-type semiconductor behavior. And then when we combine it together, we have a PN junction. And then when the light hit the PN junction, they will apply, they will induce some photovoltaic effect. Then we can obtain some voltage or something like that. So this one, as you see that there are some combination as two combination thin film. This is the top one is N-type semiconductor, and then the bottom one is N-type P-type semiconductor. This is the solar cell, and then this is the battery. Battery also consists with several layers. We have some cathode electrode. They have some addition layer. There are some current collector. There are some electrolyte, solid electrolyte, right? And then there are some anode electrolyte. As you see that those combination material will act as a battery if we combine as a thin film layer thin film. In the figure also, this is related to the thin film technology that can be used for application in the energy. Okay, and how we make the thin film deposition? How we make some the layer like this one? As Kondo Sensei mentioned before that. By using some deposition method, we can obtain some layer by layer so that we can obtain BDD sensor or something. And how we make the layer of these materials. There are some method, and I classified it into three. First is physical deposition, which means that they use physical processing. For example, like pulse laser deposition. We use some laser to heat the material that we want to make some layer. There are also molecular beam epitaxy. We use heat for this one. There are also thermal evaporation. There are also some sputtering method. This method is a thin film deposition by using physical processing. And then the second is about the chemical deposition. Chemical deposition, actually there are so many, but for example, like chemical vapor deposition or CVD, they have some classification, like plasma CVD, mist CVD, and etc. And then the second is also related to the layer deposition or ILD. Different with physical deposition, chemical deposition use chemical reaction to make a thin film. And the third one is solution-based deposition. The solution-based deposition is a very simple process, and it's similar to that how we paint some building, for example, like that. So it's very easy. If we want to make some, for example, if we want to make layer by layer of the thin film devices, for example, we can make the N-type semiconductor in the solution base. We make it as a solution, and then we just only need to spray it. For example, like they call it spray base, spray base coating or spray pyrolysis. It's similar to that how we paint something by using airbrush spray something. For example, or also or there are some classification of solution-based deposition, namely dropping base. We can call it drop casting or spin coating. There are also printing base. This is similar to that printing. How we print some figures, something like that. And then the third is the last is about deep base. For deep base is there are some classification also, namely deep coating, chemical deposition, and etc. This method can be used to obtain thin film, layer by layer of material that later they can be used for some application. For example, like a solar cell, battery, sensors, and including for the electronic devices. Okay, and some of researchers also classified thin film deposition into two: versus vacuum deposition and then non-vacuum deposition. On vacuum deposition, the process is occur in vacuum condition, which means that the deposition process, we proceed it in the vacuum chamber. For example, like this one, we want to make some, if we want to make some thin film, in this case, we just need to put all of this stuff into some high vacuum chamber or vacuum chamber. And physically position, for example, like PLD, MBE, thermal evaporating, and sputtering, those are included in the vacuum deposition. Some chemical deposition, for example, like CVD and LD, also included in the vacuum deposition. As for the non-vacuum deposition, this is all of them is related to the solution-based deposition. This means that we can proceed this deposition, the thin film deposition, just only in the ambient environment. No need to do it in some vacuum chamber. Okay. Thin film technology also, for these two slides, I discuss about the thin film deposition technique. For this slide, I discuss about what kind of the thin film we can obtain from the deposition we use. For example, like I classified into three. First is epitaxial. For the epitaxial is means we make some layer, but the layer is highly crystallized, which means that this epitaxial thin film is related to the single crystal phase. And then the second is nanostructure. The nanostructure is related to the thin film, but they have a structure. They have some morphology in the surface. And the last is about composite thin film, composite layer. And we can these three kind of thin film have their own function. For example, like epitaxy, as we get from the previous discussion, that if we have some epitaxy thin film, we can obtain a highly sensitive sensor, for example, like that. But if we want to discuss related to, for example, solar cell, we need to have some high interfaces, surface high volume surfaces, so that, for example, like a DCC solar cell, we need to have some, we need to have highly surface volume ratio, so that the nanostructure film is better compared than epitaxy. And then how about composite? The composite is material that they have different the properties will be much better compared than if they are in the single phase. Later I will discuss in more detail in the next slide. Okay, what is the thin film? What is the epitaxy? This is the first category of thin film, or layer. First is epitaxy. Epitaxy thin film is thin film with highly crystallized material, which means that it can call a single crystal thin film. Single crystal thin film. And then by using crystal epitaxial thin film, as Kondo Sensei mentioned, that we can obtain highly sensitive sensor, the BDD sensor, for example. And then by using epitaxial thin film, we also can modify the materials. By using strain engineering, that we can call strain engineering, we can modify the structure. This one, the thin film that we will deposit, and then if you see that the film can be modulated, the structure can be changed by using strain engineering from the substrate. Okay, this one, as I said before, that by using thin film, epitaxial thin film method, we can modify the structure of the thin film. And for the epitaxial thin film, also we can use some different substrate. For example, like for this one, we can obtain some modification of the thin film by using 3D. 3D, which means that 3D means that they are in the 3D system. But we also can use two-dimensional substrate to get some two-dimensional thin film, for example, like that. And then we also can combine two-dimensional film on the 3D substrate or vice versa. Yeah. As for the nanocomposite thin film, as you see that nanocomposite thin film is combination from two materials, But this two combination of two material is not they should not have some chemical reaction. Yeah? So they just a physical touch, so that we can obtain some nanocomposite thin film or layers, for example, like this. And how we make? There are some method, for example, like we can use some pattern, to make nanocomposite thin film, or we can use some self-assembled nanocomposite deposition, so that we don't need to use some pattern to make some nanocomposite thin film. And then this is the previous study, my previous study when I was in Taiwan. Yeah. In this case, we try to modify, and we try to develop some multiferric material. What is multiferric material? Multiferric material is material with two different kind of properties. Yeah. So that, for example, this one, the material is BFO3, or BFO. We can call BFO. The BFO have two properties, in the same time. They have magnetic properties and also have electrical properties. Yeah, and then BFO3 or BFO can be used for many applications, including solar cell. Yeah, that we can call photovoltaic ferroelectric solar cell, or something like that. We also can use BFO for electronic devices. We also can use BFO for photocatalysis or electrocatalysis. But however, the multiferric properties of BFO3 is still not very good, especially for their magnetic properties. Yeah. So that we can use the thin film technology, to develop to enhance the magnetic properties of the BFO. Or even we also can increase the electrical properties of BFO by using strain engineering, as I said before. For example, like the BFO have cubic structure, or orthorhombic structure, rhombohedral structure. But by using thin film deposition, thin film technology, by using strain engineering like this, we can change the structure of BFO from rhombohedral into tetragonal, so that when we have some tetragonal phase of BFO, the electrical properties of BFO will increases. Yeah. Or if we want to make some BFO or with high magnetic properties, we can combine BFO with some good magnetic properties, magnetic material. Good magnetic material, for example, like COFA2O4. And when we combine the BFO3 with COFA2O4, we can obtain some nanocomposite like this. And then by using thin film technologies, and by using self-assembled process of nanocomposite thin film, we can obtain nanocomposite like this. Yeah, this is a layer by layer of thin film. As you see here, we have some CFO or COFA2O4. We have some strontium ruthenium oxide. We have some CFO also again here, and then this is the BFO, as I said before. Yeah, the CFO, because they have good magnetic properties, they have strong magnetic properties, they can induce stronger magnetic properties of BFO. Yeah, so that we can obtain high magnetoelectric properties of BFO. As you see that if we compare with another system, BFO in the nanocomposite film, in the nanocomposite form, they have a large magnetoelectric properties. Yeah. So this is one of the purpose of thin film technology. Yeah. First is how we develop some material, how we increase the properties of some materials. Okay. And the second purpose of thin film technology is related to how we find new materials. Yeah. Before I discuss this one, probably I will let you know about the iron oxide. Yeah. Iron oxide is a material that we can obtain in everywhere. Yeah. But the iron oxide we obtain in the nature is have alpha and then beta phase. Yeah, they have they have hexagonal phase, and then this is cubic phase. Yeah, iron oxide alpha Fe2O3 and gamma Fe2O3, they have magnetic properties, just only magnetic properties. And then, according to the previous study, if we can change the structure, the phase of Fa2O3 from alpha or gamma into the epsilon phase of Fa2O3, we can make the iron oxide with multi-ferroic properties, which means that the iron oxide will have two properties: first is magnetic and then electric. Yeah, like this one. Yeah. They have magnetic properties and then they also have ferroelectric properties. Yeah, and then by using thin film technology, by using strain engineering, as I mentioned you before, like this one, strain engineering, we can obtain the phase, the rare phase of the iron oxide, with the epsilon phase, with the epsilon, where the epsilon phase is actually cannot be synthesized, by using normal synthesis process, and then but we can synthesize the alpha Fe2O3 by using thin film technology, for example, like pulse laser deposition. Yeah. Here, the previous study of when I was in Taiwan, that we can obtain epsilon phase by using strain engineering by using mica substrate. Yeah, and then the third thing, still is the third function or purpose of the thin film technology is related to how we make some materials, new materials, including how we obtain some material that previously impossible to be synthesized. Yeah, is including epsilon Fe2O3. Yeah, there are also some materials that can be that's very difficult to synthesize or very difficult to obtain. Yeah, in nature. Yeah. For example, like holmium monoxide. What is the holmium monoxide? Holmium monoxide is material ferromagnetic semiconductor. That this material ferromagnetic semiconductor can be used for some application, especially for electronic devices. Yeah. For example, like this one, holmium monoxide. It's similar with the europium monoxide. They are ferromagnetic semiconductor. Yeah. When where they have some magnetic properties coming from the interaction between holmium, between holmium atom with another holmium atom. Yeah, holmium atom is a magnetic element. Yeah, and then we have some direct interaction magnetic properties, and then we also have some RKKY interaction magnetic properties and also spur exchange magnetic properties. So that holmium monoxide will have very strong magnetic properties. Yeah. But however, the holmium monoxide is actually impossible to be made. Yeah, it's impossible to be synthesized because the holmium monoxide, the holmium element have negative Gibbs energy, means that they are very unstable. It's very difficult to make holmium monoxide. But by using thin film technology again, in 2021, we have successfully made for the first time material, namely holmium monoxide. This one by using pulse laser deposition. Yeah, by using thin film technology, we can obtain the material that did not obtain before. Yeah, for example, like this. Now, and then this is the holmium monoxide that we have synthesized previously. Holmium monoxide by using XRD, by using XPS, by using FTIR, UV-Vis. Yeah. Those of this experiment shows that we have successfully obtained holmium monoxide. Yeah, the holmium monoxide, as I said before, that because they have the holmium itself is a strong magnetic element, so that when we combine the holmium monoxide into some rock salt structure, they will have strong magnetic properties. Yeah, and then the good thing is they also have a large TC or Curie temperature. Yeah, for example, like this, compare then another holmium base. Yeah, this one is holmium monoxide. Yeah, and this one is holmium selenide. This is holmium arsenide, holmium telluride. Yeah, or holmium antimony. Gitu. holmium monoxide have large TC or large TN. Yeah, compared than another materials that exist before. This material is exist before, and this is material that we just obtained in 2021. Yeah, and the thin film deposition also not also is not related to the how we make some materials and how we develop some material or how we obtain new materials. Yeah, but the thin film technology also related to how we fabricate some devices. Yeah. Among the type of the thin film deposition, yeah, this one is vacuum deposition. Yeah. The non-vacuum deposition will have more advantage, yeah, especially for the cost, yeah, cost and then the simple process. But if we want to make some devices, for example, like solar cell devices with a very large area, we need to use deposition method, non-vacuum deposition method. Yeah, we can use a non-vacuum deposition method. It's because related to the process. Yeah, thin film processing is very simple, and then the cost is also not relatively high, and then we can obtain large area of deposition. Yeah, so this is the thin film deposition by using solution-based deposition, which means that those deposition is occur in the room temperature, occur in the non-vacuum in the ambient condition, so that we can obtain very cheap, very cheap devices if we use this one compared than if we use compared than if we use vacuum deposition. Okay, and as you see, this one non-vacuum deposition is very suitable to make a solar cell, including for flexible solar cell. Yeah, for example, like this one, for some flexible solar cell is already been produced. Yeah, I mean the flexible solar cell is already exist. Yeah? And then how we make a solar cell, flexible solar cell, we can use thin film deposition, especially for the solution-based deposition or non-vacuum deposition. This one is the product of the solar cell integrated in the back. Yeah. This one is solar cell integrated jacket. This one is flexible solar cell, including solar cell integrated car. If you imagine that if the solar cell is rigid, not flexible, the solar cell cannot be installed into the bag, yeah, into the jacket, yeah, into the car also. So that we need to have some flexible solar cell. And then how we make a flexible solar cell, we can use non-vacuum deposition or solution-based deposition. Okay. And this is the summary of my talk. The thin film technology is complementary to existing various devices, yeah, such as electronic, photovoltaic, battery, photocatalyst device, and etc. Thin film technology is also important to explain fundamental understanding of some materials, and so that for this case, yeah, we can obtain new materials, we can develop some materials which probably they have some limitation into some material with highly valuable, yeah, with very good properties. And the third is thin film fabrication method, and various combination of material in the film can be used for many applications, so that this research, the research in the thin film area will increase exponentially. And that's all my talk today. I will give the time to the moderator, Dr. Joko. Thank you.
Okay, hello, Mr. Tata. How are you?
Yes, I'm good, Dr. Joko.
Okay, so interesting topic, yes, from Mr. Tata. Is there any question from audience? Oh, nothing. Oh, I think it's so interesting topic from you, Mr. Tata. And I have a question behalf of audience from solar cell, right? Solar cells. Is it possible for Indonesia to applicate solar cell from nanotechnology?
Yes, of course, Dr. Joko. Actually, Indonesia have some advantage because they are in the equator, in the middle of the Earth, so that they have more than 12 hours of sunlight. Yeah, so that we should use solar cell to get for the energy. But so far, Indonesia still doesn't have some what's that? Uh, Apa ya? Like some uh, organization or how do I say? For example, like industry, the industry of the solar cell industry in Indonesia is still very limited, so that we cannot use the solar cell. But it's very possible, which means that the solar cell technology in Indonesia will be increased exponentially, soon, I think.
Okay, I think solar cell from your thin nanotechnology is so potential to applicate in Indonesia. So what's benefit for us if we use the solar cell from nanotechnology compared than conventional solar cell?
Okay, for example, like in my case now, we make some material, namely CZTS. CZTS. The CZTS material is very cheap compared than silicon, actually. Yeah, if we use that CZTS nanomaterial, as a thin film solar cell, we can replace the existing of silicon-based solar cell, because the CZTS material is very cheap. Actually the problem of the solar cell is also related to the price. Now the price of the solar cell is still relatively high. So that by using thin film technology, by using nanotechnology, we can obtain new materials that can replace the silicon. Yeah. For example, like CZTS I mentioned before. CZTS is made from copper, made from zinc, tin, and then selenite. Those kind of material is cheaper compared than silicon. And the second thing is CZT is also very simple, to make. We can use solution-based method to make solar cell devices. Compared than silicon-based solar cell, silicon-based solar cell have to make silicon-based solar cell is very difficult because we need to heat the silicon by using relatively high temperature, for example, like around 900 degrees Celsius or even 1000 degrees Celsius. That's why the silicon-based solar cell is very expensive. Yeah. In my opinion, even though that the reliability of silicon-based solar cell is very good, but we can replace the existing of the silicon-based solar cell by using another nanotechnology materials and or nanomaterials, for example, like JGTS, like I said before, to get cheaper solar cell devices. That's my answer, Dr. Joko.
Okay, so that's a challenge, still a challenge for applicate this thin film nanotechnology for solar cell, right?
Yes.
And then there is one question from the audience. The question is, which type of thin film is best for sensor applications and the best method for its fabrication?
Yeah, actually, all of the solar cell types can be used for sensor application, because especially for photodetector, because most of the solar cell material is semiconductor, highly sensitive to the light, so that most of material solar cell can be used for sensor. I think for the best one should be related to the material with very sensitive photosensitive. Yeah, I think for example, like a copper-based solar cell also very good for the sensor, for the photo detector, because they have very sensitive. They are very sensitive to the light. And then the best method for its for fabrication, I think, as I said before, thin film solar cell is, I think, is the best, because thin film solar cell can be made by using simple process, compared than other method, for example, like silicon based solar cell. As I say, silicon based solar cell can be fabricated by using only high temperature, but by using thin film solar cell, if we want to make a thin film solar cell, it's just only by using solution based thin film deposition should be enough. I
Okay,
think that's
Mr. Tata,
my answer.
there is another question from participant.
Yeah.
So many question because your presentation is so aesthetic, I think. Okay, another question. Do you think thin film solar cells will take over the solar cells in the future?
Yeah, I think so,
Silicon
because
and-
thin film solar cell, actually there are two consideration, how we implement how we implement the solar cell technology. First is should have high efficiency, light conversion efficiency. This the first start, the first mandatory. The second mandatory is the solar cell should be stable. Thin film solar cell is known as a very stable solar cell. Even the stability is almost similar to the silicon based solar cell. But the good thing is the thin film solar cell can be fabricated by using very cheap fabrication method, so that we can obtain cheaper solar cell devices in the future. Even though that so far the solar cell efficiency of thin film solar cell is not as good as silicon based solar cell, but I believe that in the future, probably 5 years later or probably next year, there are some thin film solar cell with very good solar cell efficiency.
Okay, this is once more question from Aswin Azhar. So, what subcrystal lattice and crystal structure of a material has anything to do with its properties? Okay.
Yes, I think so.
Is it clear,
For
Mr.
example,
Tata?
like I will give you the example BFO. The BFO, when they have orthorhombic crystal structure, the magnetic property, the electrical properties is not very good, because the electrical polarization is not very high. But when we develop the crystal structure of BFO from rhombohedral into the trigonal, which means that they have longer C-axis. When they have longer C-axis, the electrical polarization will be very large. That's my answer, Dr. Joko.
Okay. For committee, is there a minute for participant? Sorry, for Mr. Tata?
Yeah, I think should be.
Okay. Okay. Still room for Mr. Tata to show up.
Okay.
Okay. From Laurencia Gabriel, is it possible if all of Indonesia only use solar cells as the main source of electricity?
Can you repeat it again?
Okay. Is it possible if all of Indonesia only use solar cells as the main source of electricity?
I don't think so, but I think you see, everything have a limitation, including solar cell devices. Actually, for example, like if we use all electricity source by using solar cell, I think should be not good, because sometimes, like for example, like the sun, the sun is not always every day. It's not always every day light up, gitu. But for example, like if the condition is cloudy, for example, we cannot obtain very efficient light conversion. So that I think we cannot use all of the electricity sources in Indonesia by using solar cell. But I think we can use, I don't know, probably 70% or something. For example, like as we used before, as we use now, we indeed using fuel cell. We use fuel, but some of the electrical sources also use another system. For example, like water. For example, also like I don't know. Even though in another country, for example, in Japan or in another country, they have several type of electricity sources. For example, like nuclear sources, electrical solar cell sources, electrical sources, or another sources, so that we cannot use all of the energy sources by using solar cell, I think.
Okay, Mr. Tata. So I think the solar cell can be main source, but it will combine with another source, like another source. So what the
Should be combined with another source, electricity sources.
Okay. So what about the sensitivity from the solar cell if we use a nanotechnology? Because as we know that solar cell is still a little contribution to our energy. So what do you think about it?
That's the thing. I don't know why actually, but in fact that in Europe, in Japan, they use I think more than 30% sources is coming from, not 30%. I don't, more than 20%. I think the electrical sources is coming from the solar cell. For example, like if you go to Japan, you see that most of not most, some of houses also already use solar cell, but we cannot see it in Indonesia.
Okay.
That's the my answer,
Still
Dr.
room
Joko.
for Mr. Tata, committee? Okay.
Yeah,
Okay.
actually there are some question left. Yeah.
Okay. Please, committee, scroll it up. Can you scroll it up?
I think for the
Okay.
Aswin Ashar question, I think I did not yet complete answer it.
Scroll it up, committee. Okay.
Yeah.
This is
I think I
continue
will
from
read
Aswin
it from
Ashar.
here.
Okay, why in BFO with such arrangement it can have multiferroic properties?
Okay, because BFO contain two kind of element that they bring their own properties. So for example, like iron, iron they bring magnetic properties, and then bismuth, they bring some electrical properties. Yeah. When we combine bismuth and iron, they will have magnetic and electrical properties. Yeah. They couple each other. For example, like if we give some magnetic field into the BFO, the iron will spin. Yeah, will change their will modulate, will alter something like that, and then the alteration of of the iron, the atom of iron will change the position of the bismuth, and then from that interaction, the bismuth will produce some electricity.
Okay, the last question, and can it be substitute with? Sorry. Okay, and last question, and can it be substitute with other elements and still have such properties?
Yeah, it's also possible. For example, like bismuth. BFO is contain bismuth and iron and oxide, right? And BFO, so that bismuth, iron, and oxide. If we replace bismuth with some element, for example, like plumbum or Pb or lead, we also can obtain still very good composition, multiferroic, because plumbum itself, the radius of the plumbum almost have similar radius to the bismuth, so that they will give some contribution, electrical contribution also. Or we also can substitute iron, iron with cobalt. cobalt have stronger magnetic properties compared than the iron, so that if we replace iron with some cobalt, we can obtain higher magnetic properties of the BFO.
Okay, I think the presentation from Mr. Tata is finished. But before it's finished, we can display the certificate.
Okay. Thank you, Dr. Joko.
Okay, thank you, Mr. Tata. Thank you for amazing presentation. Have a nice day, Mr. Tata. Thank you.
Yeah, you too. Thank you.
Once again, thank you Mr. Tata and our moderator, Mr. Joko, for the interesting session earlier. Ladies and gentlemen, we will have a 15-minute break session. There will be also a video profile and committee announcement following this. Thank you.
Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini.
Welcome back, ladies and gentlemen, to ICATAM 2023. Moving on, we will proceed our third plenary session with the third topic, DC microgrids for better and cleaner energy utilization. For this, let us please welcome our moderator for this session, Ms. Rizky Astari Rahmania, MSc.
Good morning, everyone. I'm so honored to be here today in International Conference of Advanced Technology and Multidiscipline 2023. My name is Rizky Astari, and I'll be your moderator for this session. Our third keynote speaker today is Dr. Ramon Zamora. Good morning, Dr. Ramon. How are you today?
Good morning.
Hi. Welcome to ICATAM 2023. I'll introduce Dr. Ramon to the audience. Dr. Ramon Zamora is an associate professor at Auckland University of Technology. He received the PhD degree in electrical engineering from Washington State University in 2015. His research interests include power system modeling, simulation and control, energy management, and controls, power electronic, and renewable energy applications for power system, grid integration of renewable energy and energy storage, microgrid and smart grid, as well as smart grid and sustainable energy for greater applications. Our topic for this session is DC microgrids for better and cleaner energy utilization. Now, without further ado, I'm delighted to welcome Dr. Ramon Zamora. Please, the stage is yours.
Thank you.
Okay.
Hello, everyone. Thank you very much. Thank you for attending the presentation today. Today, I would like to present our research here about DC microgrid for better and cleaner energy utilization. I would like to introduce about DC microgrid first, and then move on to different topology of DC microgrid, and then control method in DC microgrid. And finally, I will present our research study about home energy management system, and some publication and references. So what is DC microgrid? DC microgrid is basically a small-scale power distribution system, and it is entirely DC. And why we would like to have DC? Because basically a lot of renewable energy sources are DC. So like solar energy, and then fuel cell, and even the one that is not DC, also it's better to convert to DC because they not necessarily produce the same frequency as our power system. So when we need to convert to make sure the frequency is matching, then we need to convert them to the correct frequency, or better to convert them to DC. Yeah. So here, configuration of DC microgrid. There is one DC bus here where everything is connected, and this kind of microgrid has the ability to connect to the grid or interconnected system, or also can be autonomously operated. When there is some problem with the grid, they can island. So operating as islanded, and by disconnecting from the main grid. And so as I previously mentioned, there is
big advantages here because a lot of renewable energy sources are DC, and also we don't need to worry about frequency here, and also we don't need to worry about reactive power. And basically, as we all know, there are a lot of concern about cleaner or more environmentally friendly sources and reducing carbon emission, basically. So if we see here, the fossil fuel-based generation produce tremendous amount of gas emission, while renewable energy sources pretty much negligible in terms of carbon emission. Okay, and if we see the trend by 2050, or even before that, actually by 2035, renewable energy sources already basically balanced with non-renewable energy sources, and it will keep increasing. And because of this, basically, we need a system that can accommodate these various renewable energy sources. When we talk about renewable energy sources, we talk about different sources, and these different sources have different characteristics. And to optimally connect them in the system, we need a system that can accommodate them. And this is best accommodated by microgrid. And one of the advantages of this DC microgrid is that to accommodate different type of renewable energy sources. And there are different type of microgrid. In general, there is autonomous basic, autonomous full, and interconnected community. These are the table here shows the different stage of development of different type of microgrid in different region all over the world. Okay. And what is autonomous basic? Autonomous basic is basically isolated microgrid that cannot accommodate the load for 24 hours a day. So this is maybe for rural areas where not enough resources, but they still can be accommodated partially by having autonomous basic DC microgrid. And autonomous full, of course, still autonomous, isolated system, but they can accommodate the load for 24 hours in a day. While interconnected community is a bigger system, they are interconnected, and usually like big communities, short big communities. It could be interconnected to the grid or just among the communities itself. Okay? And in some part of the world, there are mixed stage of development. For example, in autonomous full here, in East and South Asia, they are existing in different stage of maturity. So this is possible to exist. Still limited, and then there are some pilot, and also there are some emerging. So depend on the development in that areas. Okay. We have been talking about advantages and also development in all over the world with different type of microgrid. Now, in specifically about DC microgrid, there are different topologies of DC microgrid, and these topologies are, have specific characteristic or specific function, and all also are also suitable for specific size. Okay. So basically, there is single bus topology, multi-bus topology, and so on. So we start with the very simple thing, which is single bus topology. And this single bus topology, basically, there is one DC bus here. So all the sources, load, and energy storage connect to one DC bus. And there is additional information here saying it's passive type. What is passive type? Passive type means that energy storage system here is passively connected to the DC bus. There is no control. It just connects over there. And it means the DC bus voltage here must match the energy storage voltage level. Okay. And this is very simple and low cost topology. And then single bus topology with active type, and basically the same as the previous topology, but only it is active now. There is a controller for energy storage system. So there is bidirectional DC-DC converter here, and this allow us to regulate the charging and discharging of the energy storage system here, and also allow us to connect energy storage system with different voltage level from the DC bus here. And the next topology is bipolar single bus topology. So basically, the bus here still only one DC bus, but this DC bus can have different polarity. So can be positive, negative, and zero. And this allow connection for different voltage level. For example, we can connect positive 170 volt or negative 170 volt, or between positive and negative become 340 volt, like that. Okay. And next is multi-bus topology. And this multi-bus topology basically allow different DC bus. So for example, here there is DC bus 1, DC bus 2 here, and so on until DC bus N. Okay. So basically, each DC bus here is an independent microgrid, or can work independently, but they connect to the same bus to form one entity of bigger microgrid. So like multi-microgrid system, basically. And then they can connect to the grid all together. So basically, the advantages here is one microgrid can help the other microgrid, and also we can have a transactive energy system among the microgrids here. Okay. And the next topology is multi-terminal bus topology. And this basically allow or have a different bus in the one system. We can connect at different bus. Okay, and this different bus might also be at different voltage level. Okay, for example, like here, the load is connected at this bus, while energy storage system is connected at this bus, and wind energy connected at this bus. Of course, as I previously mentioned, it allows a connection at different voltage level, and this voltage level is regulated by DC-DC converter here, or DC-AC converter here. So they can have a different voltage level, or of course, I mean, like then there might be something to connect between different voltage level to the other buses. Okay, so if I mean, like if we allow connection at different voltage level here, and then additional information may be needed. Okay. And next is a ring bus topology. Here, basically, a system connected in a ring form, and this topology is basically allow a reconfiguration of the system such that a system can have a better reliability. If there is any fault in the system, then only a part of the system that is faulted will be disconnected from the microgrid. And the supply or power delivery can reroute it to the other part of the system. Okay. And now zonal topology. This zonal topology is basically focusing on the load. The load can be located or cluster into a specific zone. So like here, there are some load in zone 1 and then some load in zone 2. And this topology is commonly used for shipboard power system. So one example of microgrid is like a shipboard power system. So like electric ship, basically. And this shipboard power system can be common like civil application, can be also military application, depending on what we have. Okay, but again, depending on the function, the load here might be also might have different characteristic. So, like for example, in the military application, maybe there is impulse kind of load when the ship like firing the gun. So then we need to understand how much maximum load when the firearm is triggered, and how much average load. Then we need to size the microgrid accordingly based on our understanding about the load inside the microgrid. And similar to the previous one, of course, when there is a fault, we can isolate or reconfigure the path inside the microgrid by opening and closing the breaker here. Okay. And next, we will continue with the control method in DC microgrid. So basically, there are several control methods in DC microgrid, and this control method basically common, not just for DC microgrid, but we adapt it and implement for DC microgrid. So here the basic control method is decentralized method, where each local controller, so for example, this here, there is one controller for DC-DC converter that is responsible for this energy storage. This local controller here basically just receive the local measurement and doesn't know anything about the other part of the system, just from local or this bus here, and also the energy storage here. So just whatever it is responsible to control. Okay. And the other local controller also responsible for each own part to control. And the good thing here is local controller does not need any communication network and can operate autonomously without worrying or considering other measurement in the other part of the microgrid. And the disadvantages of this, of course, the system might not be working optimally because individual local controller will act individually. Okay? And for centralized control, this is more complicated. Basically, there is one microgrid central controller. So microgrid central controller will coordinate the local controller, and then the microgrid central controller will need also to receive information from the lower level control. Okay, so basically there is some information or some measurement needed to be sent in the among different layer in the system. Okay, and also there is information or control action need to be dispatched or sent to the lower level control. Okay, and there is also disadvantages here in terms of if there is any fault or malfunctioning of communication network, then the central controller will not be functioning. Okay, will not be functioning, and this is called single point of failure. And this is something that we need to consider whether we allow that to happen or we need to mitigate it by considering the other type of control. Okay, and next type of control is distributed control. Distributed control somehow combine between centralized and decentralized control. So basically, it needs communication to optimally control the entire system, but also allow if a communication network not operating perfectly or malfunctioning, then the local controller will take responsibility. Okay? And basically, when we talk about different type of control, it is basically not saying that one is superior compared to the other. It's not like that. Even microgrid itself, also when we talk about microgrid, it's not that big microgrid is better compared to small microgrid. It is just about what we need, basically. Like, for example, like small island need only small microgrid, for example, or one shipboard or system, for example, it just need that size of microgrid. We don't need to increase the size. So basically, what we do here is basically seeing what problem we have or what object, and then we provide a solution for that specific object, okay, or for that specific problem. So when we talk about different type of control as well, basically decentralized control can be used for power or current sharing among different distributed energy resources or distributed generation. And for centralized and distributed control can be used for voltage resolution or state of charge balance. Okay. So because of different type of sources and also different type of load inside the microgrid, also different function of the system inside the microgrid. For example, some want to optimize efficiency, some want to minimize cost or something like that, or some want to minimize carbon emission. Then because of that, then it is better to combine different type of control into the microgrid. And to combine this, the best way is to have hierarchical control, where we can have a decentralized and centralized approach in the microgrid. Okay. And in this hierarchical control, we have a different layer of control. The first layer is primary control, where we have power current sharing and also voltage control. And then second layer, we have voltage restoration as a if you work in power system, you must be familiar that if there is any addition of the load, then frequency will decrease. But since we here work with DC, there is no frequency, and the changes here will be on the voltage. Okay, so increasing, decreasing, the load will change the voltage. And this voltage will stay at the new voltage level. So basically, let's say we work with 480 volt DC, and then if there is any increase of the load in the system, the voltage will decrease, and this decrease in the voltage will basically will will cause the system work at off nominal, not at the nominal frequency. And then basically we need additional control here, secondary control, to restore the voltage again to the nominal. Okay, so if we just use primary layer of control, there is no voltage resolution, and it will keep operating at off nominal. So the function of secondary control here to make sure that it will operate at the nominal condition. And tertiary control is higher level control, it work long term, and usually it work for optimal energy scheduling and cost minimization and so on. This is the optimization is at this level basically. Okay. And if we see in terms of time frame or fast response, time response, basically primary control is in the order of 10 to 100 millisecond, while a medium, secondary control is a medium fast response between 1 to 10 second, and tertiary control is more than 5 minutes. Okay. And this is primary control here. So this is an example of primary control. So basically, when we, as I previously mentioned, the increase of the load will change voltage here. So basically, we have two equations here. So the voltage here, the output voltage depend on the reference voltage and then also the drop of the current and the output current. And the second one is the output voltage of the DC microgrid depend on the reference voltage and drop of the power and the output power or load power in this case. Okay, because output power is depending on the load power. And basically, we can switch between power-based drop or current-based drop, depending on the operation condition. Okay, so either like power-based drop or current-based drop can be used, but both the drop will basically will give the reference voltage to the inner loop voltage. This inner loop voltage basically is the built-in control in inner loop control. The inner loop control is basically the built-in control for voltage and current inside the converter basically. And for secondary control, as I previously mentioned, the main function here is to restore the voltage. So basically, the output of this secondary control will be the delta voltage that is needed to for the inner loop control to increase the voltage. So basically, the secondary control will give the delta voltage, and this delta voltage will be compared with the reference voltage, and then it will give a command to the inner loop control to increase or decrease the voltage. Okay. So basically, since this voltage restoration, basically, when we talk about microgrid, and if there are different distributed generators inside the microgrid, and this will need to coordinate among distributed generator, and then we need local communication, and this malfunctioning or communication delay will affect the performance of this secondary control. And what we do usually, we simulate this condition, the communication delay, and also the faulty of communication network we simulated whether it will affect the system performance or not. And also we propose some mitigation method such that the system can operate regardless of this communication delay or malfunctioning. Okay. And this is about the tertiary control, or basically in microgrid system, we call it energy management system. And this energy management system basically will make sure that the optimal condition is achieved. Yeah. So some example here is basically optimal in terms of generating power or minimizing cost or minimizing carbon emission. Okay. And when we see all these control method in one system, basically the relationship is like this. The output of the tertiary control will be input or reference for the secondary control, and then the output of secondary control will be input to the primary control. Okay. Okay. Now we would like to talk about some or one case study with some technical simulation here. So basically, okay. So basically, this is an example of hybrid energy management system, and we use this for intelligent home energy management system. So the example here is this is a load here, and the load here there are three type load. Basically, constant power load, and then resistive load and fast load. Okay, and also here we have supercapacitor here. We have supercapacitor here, and we have a battery here. Okay. We have supercapacitor and we have battery, and basically the battery here will provide the system with long-term energy, while supercapacitor will just respond instantaneously because of the difference characteristic between battery and supercapacitor. So one have high energy density, which is battery, and the other one has high power density, which is supercapacitor. Okay, and if we see here the control diagram here, basically representing this equation. So the battery voltage will be controlled based on reference voltage here, and then also input amount of power battery generated, and then also a delta voltage of the battery, and also the line voltage, because we need also to consider line here, different impedance for the line. Okay, while supercapacitor here, the output voltage of supercapacitor depend on reference voltage and output power of supercapacitor and delta voltage of supercapacitor and also line voltage of supercapacitor. Okay. Basically, here the drop here, the drop is here, M here is drop, and N here is drop. So the drop for supercapacitor is different from the drop of the battery. Okay, and okay. So based on that case for supercapacitor, battery, and different load, basically we try to analyze if the capacitor of the supercapacitor and the battery. So basically here CB and CB here and CSC here, because this is the voltage. I mean, the voltage of battery is across the CB here. The voltage of supercapacitor are across of CSC here. And this CB and CSC will determine the DC bus voltage here, and load is connected here, basically. Okay. So when we have 100 microfarad of the capacitor for both of them, and we see the characteristic, basically body plot here, and we see the magnitude of this. Basically, this is the output impedance characteristic, basically, and we see that at low frequency, the output impedance of the system basically behave almost the same as the output impedance of the battery. Okay, so if we see here, the output impedance of the battery is the blue color here, while output impedance of the system, the impedance of the battery is blue, and then the impedance of the system, the entire system, is yellow here. Yeah. So at low frequency, it is basically almost the same. Okay, but at high frequency, it is basically close, but not exactly the same as the supercapacitor. Okay, why we do this? Basically, as I previously mentioned, battery is high energy density. It means that it will not respond to high fluctuation of the load. Okay, high fluctuation of the load cannot be responded by battery, but battery will continuously produce enough energy to the load. Okay, so basically, battery behave well or perform well at low frequency. Okay, but then supercapacitor, on the other hand, is high power density. It cannot really sustain energy, but it can respond to high fluctuation of the load. Okay. So what we do is now we increase supercapacitor impedance and keep the battery supercapacitor capacitor, the capacitance value of supercapacitor of the supercapacitor circuit, I mean, and then we keep the battery capacitor, and we'll find it the behavior is now basically at low frequency the system should exactly the same impedance as battery, while at a high frequency, it exactly or very close to supercapacitor. So this is the correct setting of capacitor in the circuit. Okay? And then when we have that, we use that setting, and then we change some characteristic to make sure that our system still behave or perform correctly. So we change omega SOC, and also we change key SOC. So some parameter in the circuit, in the control, and we see that the system still behave correctly. Okay, and also we also change ESC and EB, the voltage of the supercapacitor and voltage of battery, and we will still find the correct characteristic of the system. Okay, and based on that, then we use that setting to see the performance of the entire system. So basically, we in figure A and B, we have different, or we show the load characteristic, so changing of the load, and then also charging, discharging mode of the battery, okay, and supercapacitor. So if this is the load, and then the battery and supercapacitor basically will respond to the increase and decrease of the load, and we see that at the when the load change, the supercapacitor will respond quickly, but then it will not supply anything later. Okay, and then we want also to make sure that the battery have balance SOC. So basically, SOC here is state of charge, and we want to make sure that if we have several batteries in the system, the state of charge of the battery should converge to the same point. Not one is very high, one is very low. So we see here that it is successfully achieved, basically. And also for the supercapacitor as well, we successfully achieve the state of charge convert at some point. And the voltage level of the DC bus voltage also relatively constant here. Okay, that's all from me. And these are some journal publication that we have, and also conference publication based on this specific research from the case study. Okay, thank you very much. And
thank you, Dr. Raman Zamora, for the interesting presentation. Now we are in the Q&A session. We are doing one question at a time. Actually, we have already received some question. I'll read it out for you, okay? First question, what is the stability challenge that may arise in DC microgrid?
Okay, yeah, the stability challenge is of course related to the change of the rapid change or a big change of the load or generation. Okay, the load of generation, and basically this is almost similar to the big power system, but the thing here, because we don't have frequency, we don't need to deal with frequency. So the stability challenge here is related to the voltage only. So basically, it is simpler because we just need to focus on the voltage here. So there is no frequency stability challenge, and there is no rotor angle stability challenge. So just basically voltage stability. Okay, so it is simpler, but the rule of thumb, of course, if there is any imbalances or rapid change in the system, then it will bring some challenge in terms of stability. But as I presented here, we size battery, and then we size also supercapacitor, and we hope that both combination and battery and supercapacitor will take care of rapid change in the system. Okay.
Thank you.
Thank you.
And the next question is the concept of primary, secondary, and tertiary controller in the DC microgrid is similar to the frequency control in AC system?
Yeah, it is. It is actually basically not just DC microgrid, AC microgrid as actually basically the chronological order is like this. Basically, we have power system. Our engineer understand power system very well, and then when we introduce new concept, we need to take this into consideration that people understand conventional power system. So something that we introduce need to build up based on that. So yes, to answer that, it is, based on basically primary, secondary, and tertiary control in conventional power system.
Okay.
Yeah. But the only thing is, since we work with DC, we don't need to worry about frequency. That is, then we just need to take care of voltage only. Thank you.
All right. The next question is it essential to have inertia in DC microgrid?
Inertia here, basically, not the same as inertia in the conventional power system. So since DC microgrid basically DC, and we don't, when we talk about inertia in power system, it is somehow we recall something like swing equation, right? And this swing equation is related to rotating mass, basically. And in DC microgrid, basically, we don't need to worry about that. But inertia here is in the form of synthetic inertia. So inertia is still, not exactly the same, but there is something that we need an entity inside the DC microgrid that respond the change of energy or power. Okay, and this is in my presentation represented by battery and supercapacitor. This battery and supercapacitor basically is with its controller, with their controller representing synthetic inertia.
Okay. We have another question from Suta Laksana. The question is there any specific reason why you use impedance-based analysis for DC microgrid?
The reason here is basically just to size the component in the system to make sure that when we intend to have that the high fluctuation of the load will be responded by supercapacitor, while low fluctuation of the load will be responded by battery. Okay, so basically it is more about developing correct model for the entire system, such that our battery will not push to respond high fluctuation of the load, and our supercapacitor will be able to respond low fluctuation, high fluctuation of the load. So it is just about correctly sizing the entire system such that the component will function according to its characteristic, not push to respond to different characteristic. Okay.
Okay, thank you. Actually, that was the last question. And
Yeah.
if the audience still have things to discuss with you, may they reach you via email, I think?
Yes. Yes.
Okay.
Sure. Yep.
Thank you. So the audience, if you still have questions or things to discuss with Dr. Ramon Zamora, you can reach him via email. On behalf of FTMM, I would like to say our gratitude for you to come here, and then I'm going to take this opportunity to give our token of appreciation.
Thank you.
Dr. Ramon Zamora.
Thank you.
Thank you all for participating, and I'll give back the stage to the Master of Ceremony.
Once again, thank you, Dr. Ramon Zamora, for the interesting session earlier. Moving on, we would like to inform the audience to don't forget to fill out the attendance form that will be shared by the operator. And for the next, there will be a documentation session, so the participants are expected to turn on their camera. So ladies and gentlemen, please turn on the camera so the documentation session could be started. Moving on, we will have a 60-minute break session for prayer and lunch break. So the audience are expected to be back at 1 o'clock Indonesian time. After this, participants please move to the parallel session 1, 2, and 3.
Recording stopped. Recording in progress.
senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. ICATAM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. senantiasa berjalan. Zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. ICATAM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi.
Recording stopped. Recording in progress.
Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. ICATAM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi.
Hitung ya. Siapa nih? 1, 2, 3.
Welcome back, ladies and gentlemen. For this next session, we'll be having an exciting news which I'm sure most of us couldn't wait.
That's right, Ziva. Now we will have the announcement of the best presenter of ICATAM's 2023. There will be winner from each day, day 1 or day 2.
Moving forward, ladies and gentlemen, for the first day in parallel session day 1, the winner for the best presenter of ICATAM 2023, drum rolls please.
Congratulations to
Mr. Awan Uji Krismanto with the topic about probabilistic analysis of voltage stability of distribution systems. Is Mr. Awan present with us? Mr. Awan, please be... Okay. Unfortunately, Mr. Awan is not here with us, but we will still share the certificate.
Moving on, we'll have the announcement of the best presenter, still from the day 1, from parallel session 2, the winner of the best presenter of ICATAM's 2023. Drum rolls. Congratulations to Zafirin Ramadana with a topic an investigation to the effects of simulation game playing as a pre-training enhancements before driving simulator exam for the licensing purposes. Is Mr. Zafirin Ramadana are present with us?
Please turn on your camera if you're present with us.
Unfortunately, Mr. Zafirin Ramadana is not here with us, but we'll be showing the certificate of appreciation.
Okay, once again, congratulations to Mr. Zafirin. Moving forward, we'll be having the announcement for the third parallel session for the first day. And the winner for the best presenter of ICATAM 2023, drum roll please. Congratulations to Ms. Maria Anityasari with the topic about assessing the benefit cost ratio (BCR) of smart street light system (SSLS) about a case study of Surabaya City. Is Ms. Maria present with us? Please turn on your camera if you're present with us. Okay, unfortunately, Ms. Maria is not here with us, but we will still show the certificate of appreciation.
Moving on, we will be having the announcement of the best presenter of ICATAM's 2023, to be precise for the day 2. Well, from the first parallel session, the winner of the best presenter, drum rolls please. Congratulations to Brastira Yuva Wardana with the topic nano diamond material for sensor application.
Is Ms. Brastira Yuva present with us? Please turn on your camera if you are. Okay, unfortunately, Ms. Brastira Yuva is not present with us, but we will still show the certificate for appreciation. Once again, congratulations, Ms. Brastira Yuva. Moving on, we will announce the parallel session 2 for day 2, and the winner, drum rolls please.
Congratulations to
Mr. Fasi Bintang Islami with the topic about green synthesis of star-shaped composites for photo antibacterial therapy. Is Mr. Fasi present with us? Okay, unfortunately, Mr. Fasi is not present with us, but we will still share the certificate. Once again, congratulations, Mr. Fasi Bintang Islami.
Moving forward for the parallel session 3, with the winner of the best presenter of ICATAM's 2023, drum roll please. Congratulations to Ratna Sari Dewi with the topic integration of the FMEA method with FRAM for work accident risk analysis in packaging manufacturing.
Okay.
Is Ms. Ratna Sari Dewi is available with us? If you are, please turn on the camera so we could start the documentation session.
Okay, unfortunately, Ms. Rati is not present with us, but we will still present the certificate of appreciation. Once again, congratulations, Ms. Ratna. It's Ms. And that is all for the winners of the Best Presenter of ICATAM 2023. Once again, congratulations. And moving forward, unfortunately, ladies and gentlemen, we have reached the end of ICATAM 2023 event. It has been our utmost pleasure to guide the event since day one, and we hope with ICATAM 2023 theme of nanotechnology and advanced technology for a sustainable future, we can gain more knowledge and new information from what we have acquired from this event, so that we can even innovate future projects that can help sustain our environment.
With this, we close the International Conference on Advanced Technology and Multidiscipline 2023. Once again, my name is Yudison Jandra Tanamal, and here with me,
and I'm Zifa Sholima. We, as the Master of Ceremonies, take our leave.
Thank you and see you in ICATAM 2024.